as a means of also talking about something else, okay? So in the swing question, and I'm just gonna, there's a couple of assumptions that we're gonna make right now that we will no longer be able to make next semester. So I'm saying that on purpose because we need to start paying attention to, as things change, our concept of this stuff has to evolve too. I'm really struggling in trying to convey to you that you need to remember the old stuff. And that's been hard because as I talk to folks, it's like they forget everything the moment the test is done. We can't do that here. So right now, we assume that our objects are point masses. I've been saying this for a little while, but I want to reiterate it because it's more important here. What I mean by that is that the mass is concentrated at a single place. This is a kid on a swing. That's not really true, right? I mean, the kid on the swing would be something big. And so their mass would take up a larger section of this. And that does play a role. Where do we choose to measure things like the height above the ground? Do we measure it from their bottom, or do we measure it from their top, their middle? And for stuff like this, it's not that big a deal. We could probably just pick one point and stick with it. But we know that as this person is pulled backwards, their orientation also changes. And that does actually affect the answer. That's the whole reason why you can pump a swing. And anybody who's ever been on a swing and been able to get it to go, you understand that there's a certain thing you have to do. And if you know what that thing is, you can make the swing work. Well, that involves you changing the orientation of your body. So if we get away from all that and we assume that this is a point mass, then we're focusing on the idea that everything is going to be related to where this point mass moves to. In this problem, you're applying a force this way. And in doing so, you're hoping to not only pull the swing back, but lift the swing up. Does everybody recognize that? Now, you actually never pull upwards on the person. You're just pulling to the side on the person, but the consequence of the forces acting on the person pulls the person upwards. But I want to be very clear, you're not pulling them up. You're pulling backwards, right? Horizontal the whole time. I don't know what question A says, but it's probably something about find a relationship between the size of the force and the angle that the swing makes.
What is the force applied on the adult? So for the person pulling.
So it's the same question. And let me help you with what might be on your next test. This question I'm asking right now is how I would really want to phrase it for a test. Find a relationship between the force you apply and the angle the swing makes. That's probably how I would phrase it on the test, and I think that's a harder phrasing, but that's kind of the way they're going on the AP exam. So I think there's some things about this that we already know. It probably will get more difficult to keep pulling the person back the further you've already pulled them back. Does that make sense? Does that sentence make sense? So like when you are here, it doesn't take any force for the person to be here. It takes some force to have pulled the person back to here. But I believe it will take more force to pull the person back to here. I think our relationship will show that as theta gets bigger, the force required to pull this person back also gets bigger. That's what I think. Now, the question says just to find out what the force is, but you will be finding a relationship if you do it this way. So I'm going to pick one of these spots. Let's pick this one to draw a free body diagram. There's a force this way. There's a force this way. And there's a force that way. Agreed? Assuming that we are looking for the minimum force necessary, these forces are balanced. All right, we want what force would hold them here. So I'm going to choose a coordinate system aligned like this. That makes this equal to theta. And that suggests t cos theta this way and t sine theta this way. Any question about that? T is a placeholder here. We weren't asked for the tension. We're asked for the force. I'm going to use the tension as a placeholder. So net force in the x is 0. So t sine theta equals F. And net force in the y direction is also 0. So t cosine theta equals mg. So it looks like the force equals mg tangent theta. Now, you should pay attention to this function. This is a function for the size of the force required to pull the child backwards as the angle increases. Do you notice you could never pull the child back 90 degrees? Right? Do you see why that's true? If not, you're not paying attention, and that's the kind of problem that's going to show up on the test, and you're not going to be able to answer it, and you're going to feel like physics is hard. But it says it right there. Tangent has limits, and it approaches infinity as theta approaches 90 degrees. So the only way that you could ever pull perfectly 90 degrees is if you pull with infinite force. That's never going to happen. And the reason is simple. If you get 90 degrees, there has to be some force that's pulling upwards on the kid. And if you pull at 90 degrees, there's no force pulling upwards. So that's why you can't actually do that. In fact, by the time you reach 45 degrees, you're already having to pull with their weight. I don't know if you guys have ever taken a kid to the park, but you probably would not pull perfectly horizontal. You would probably pull a little up on them because it's a little easier. But that's not what the problem is about. So that's question A, or first question. Is there more to it? I'm sure there is.
Find the tension.
I can solve for the tension immediately without having done all that work. Because right there, the tension is in terms of mg and theta, so I can get a relationship for tension right here. That one's pretty straightforward.
Can we just write that as secant?
What's that?
Can we just write it as secant?
Yeah, that's fine. You will almost never see me write secants or cosecants on the board. But there's nothing wrong with it. I'm just not adept at it. It's a limitation of mine. All right, is there any more to this problem?
Yeah, it says if the adult releases the child, what's the tension removed when the child passes through the release?
All right. I like this part of the problem the most. You can probably imagine why. But on an actual AP exam, there would probably be a couple of intermediate points here. But this is the kind of problem that they really like on the AP exam. And yeah, this is testable. This is the kind of stuff you need to be prepared for. All right? That is different than what's here. All the stuff about force probably is a distraction. So I want to clear this out and talk about what is really going on with this question. This question suggests two states for me. So let's reduce this so it's a little bit easier by maybe getting rid of some of the stuff that's here. I want to exaggerate this, so I'm trying to make sure that I have the two states pretty far apart. So let's say that we pull the child back this angle theta, and we release them, and we're trying to figure out the tension when we make it to here. It's not an accident that they're asking about the tension at the bottom. The reason they're asking about the tension at the bottom is because at the bottom, there are only two forces, and one of them's up and one of them's down. And so it's a very strictly uniform circular motion problem. So that's why they ask about the bottom. In a lot of these circular motion problems, they ask about the bottom or the very top, and that's on purpose to make the math a little bit easier and less confusing. They don't have to, but that's what they generally do. At the bottom, there's two forces acting on the system. There's going to be tension upwards and weight downwards. They have to be unbalanced because the kid on the swing is traveling in a circular path. So I would start this problem probably where you guys did, which is to assume it's a uniform circular motion problem at the very bottom. And to set upwards as positive and write tension minus weight equals m v squared over L. I'm saying L because that's the radius, right? The length of the string.
Yeah.
Now, I can't get an answer here unless I know the velocity. So we need a way of finding the velocity. This problem should scream energy to you. It should scream it. If you look closely, the object starts at one height and goes to another height. That looks like it starts with gravitational potential energy. If I make the bottom the reference level, then I can make a comparison between the amount of energy the object has at the top of its motion with the amount of energy it has at the bottom. It should be the same. Now, if you're asking, but why can I do that if it travels along this path? Well, remember, the gravitational force is path independent. That path is just like the path of a slide. It doesn't make any difference how it gets there as long as there's nothing that takes energy away from the system. So I'm not sure if that's a confusing factor for you or not. Do you guys see why we can compare these two states? Or do I need to explain it anymore? I would like to point something out. There are two forces acting on the kid as he swings from this point to this point. Two forces, tension and weight, right? The parent let go, so it's just tension and weight. Both of them can do work on the system, but only one of them does. Gravity. I would ask this question on a test just to see if you're paying attention. So please consider writing this down. The tension can't do work on the system. I'm going to tell you why, but the tension can't do work on the system. This is a teachable moment. If you look closely, the tension has to be in this direction, along the string. But the displacement has to be this way, right? The tangent to the curve, which means it's 90 degrees between the tension and the displacement. So the tension can't do work because it'd be the cosine of 90 degrees. Gravity can do work because it doesn't have that problem, but tension can't do work here. This is a good question, and it's one of those ones where I would say, does tension do work? Yes or no? Justify your answer. And the justification would need to be that the tension acts perpendicular to the displacement. That would have to be your response. Okay. I think the next hardest part about this, and you might wonder why I'm taking so long to do this problem, because this problem shows up on the exam about every year. It's worth us spending the time on. You need to find a way to express the height in terms of the angle. Right? We're not allowed to have h in our answer. We don't have an h, but we have an angle. And if you know how to do this, great, go with it. If you don't know how to do this, you should look at the geometry. So how many of you need me to explain to you how to get h in terms of the angle? Nobody? Okay, a couple of you. I'm happy to do it. If you don't know how to do it, if you don't know what I'm asking, then you should be able to do what I'm about to show you. But at the end, I would just memorize it. You don't have time on the exam to prove it. Does everybody understand? If it was AP 1, you can figure it out. But on the AP Physics C exam, this is worth memorizing. I need a different picture so that it's not compromised this way. So I'm just going to, over here, h is going to be L times 1 minus cosine theta. Set that aside. And it looks like I can set the gravitational potential energy here equal to the kinetic energy down there. This sounds like a way of figuring out what 1/2 mv squared is. So mg L times 1 minus cosine theta. Right, this is my gravitational potential energy. Has to equal 1/2 mv squared. Everything good so far? I have an mv squared here, and I have an mv squared here. So is that okay? I just make that, so I'm gonna solve that for mv squared and get 2 mgl times 1 minus cosine theta equals mv squared. All righty. This is a bear of a question, isn't it? Compared to A and B, part C is just brutal. T minus mg equals 2 mgl times 1 minus cosine theta, all divided by L. You might feel as though you could stop here, but remember, you're supposed to be solving for T. So we still have to do algebra, but that's the heavy lifting, wouldn't you say? And that's all the hard work. Everything else is algebra. It does clean up rather nicely. So if you are interested in doing the math, and I would recommend cleaning it up a little bit, at least cancel the L's. And I like to factor out the mg, because then you get 1 plus 2 minus 2 cosine theta. So you can combine like terms and get mg times 3 minus 2 cosine theta. I think you'd probably be okay if you stopped here on the AP exam, but I like this one too. How do you check if you're right? Well, this is mg, that's a force, so that's in newtons, and all of this is unitless, so at least my units work out okay. All right, question number 1 was a lot. I'm pretty sure most of them were a lot, but that one was a lot. Do another one? Yes. Moving right along. I don't know what 2 is either.
It's the hill and then the bottom of the hill. The car goes up the hill and then the car goes like a dip. That's like the second part of the problem. And then it asks for like the maximum velocity.
Maximum velocity at the top of the hill, bottom of the hill.
It just says velocity. The first question.
Is this what it looks like?
No, it's two separate problems. A car passes over the top of a circular hilltop road of radius r. If the car has a mass of m, what is the fastest speed the car can travel and still remain in contact with the road?
Okay. So this is a throwback to UCM. For the car to be able to travel here and stay in contact with the road, it's experiencing 2 forces, a normal force this way and weight this way. For it to travel in the circle, they have to be unbalanced towards the center of that circle, and I need to make downwards positive. Good so far? We've done this one. So I'm just going to keep going the way I've kind of written it. And I'm not trying to be flip about it. This problem turns up enough where it's good to repeat it. Those are the 2 forces acting, and this is a UCM problem again. We're interested in finding the velocity. So knowing that we're interested in finding the velocity, I'm going to identify a few things here. First, the velocity is here, right? Now, this is a constant. If the velocity were to get bigger, n would have to get smaller, right? Because I'm subtracting it. So what is the maximum speed? Well, if v keeps getting bigger, the smallest n can be a 0. So the maximum speed is when n goes to 0. So that's when v is equal to the root of g times r. This is v max. Don't go any faster than that. I mean, you can. There's no longer travel in a circle. You're going to be a projectile. So you're going to go like that. All right. Good one. Is there more to this question?
Yes, it's like, now, it's if the road bridge goes down instead of up, so like if the radius is.
Okay. So just,
It asks what the normal force is.
are we maintaining the same speed as before?
Yes.
Okay.
Yeah.
So down here at the bottom, the normal force must be greater than the weight. So you're going to feel this. This is when you're in the bottom of the roller coaster and you kind of do one of those because the normal force is suddenly greater than it was a moment ago. I'm going to make upwards positive, and the velocity is going to equal square root of GR. Same radius of curvature, I assume. So normal minus mg has to equal mv squared over r, but I'm going to replace v squared with the square root of gr and get m times the square root of gr squared over r, normal minus mg. That looks like the r's are going to cancel, and I'm going to get just mg there. So it looks like my normal force is going to be twice the weight. So you'll feel twice as heavy at the bottom of this dip in the road if you maintain that speed. We good? Next question on the homework? Yes, ma'am.
That's asking what the maximum height attainable is and what the object is. What's the
Okay. If that continues, I'm going to bang on the wall and say, we're working in here. So,
radius is 0.5.
okay. Do I need all that? Did they give me the velocity? Okay, and what is question, what, you said part C, so,
Maximum height attained by the block after it exits the ramp.
okay, so it's leaving the ramp right here at 4 meters per second.
Yes.
Okay, and the angle of the ramp is,
30.
and they tell me the height off the ground, don't they?
Which is the same as the radius.
0.5?
Yeah.
Okay. All right. I will give you a choice. Would you like this to be worked out using energy or like this worked out using the projectile motion rules from September? They're the same. I think energy's easier, but they're arguably the same for you from your vantage point. How about we do energy? Because there is less math. Is that okay? All right. Would you agree that at its maximum height, it's going to have kinetic energy because it's moving sideways, and it's going to have gravitational potential energy? Can we all agree with that? We don't know how much gravitational potential energy it has. That's the point. We're searching for this height. So at that point, it's going to be mgh plus 1/2 mvx squared. It only has horizontal velocity at the maximum height. Now, where it is right now, it has height, mg times 0.5, so it has gravitational potential energy, and it has kinetic energy of 1/2 m times 4 squared. Now, obviously the m's cancel out because we can set these equal to each other, but here's the thing you have to do. You have to figure out what Vx is. And Vx is just 4 cosine 30 degrees. Right? It's launched at an angle of 30 degrees. Once you put that in here, you can solve for h. It is a one-step problem, and I think that's easier than doing projectile motion. What's that? Is what equal to 1? I don't know the answer. But I'll work it out while you guys are leaving. Bye, folks. Have a good day.
I don't have a secondary.
I think there's obviously stuff like there.
I just want the seating chart in front of me.
So you get specific tutoring days, or can I just come in the morning and the day and get help or something?
I'm sorry, you'll have to say all that over again.
Do you have a specific? You said you have specific tutoring days, or can
I have a calendar of them.
or can I just like come in the morning whenever I need help or whatever?
You can come in. I can't always guarantee I can stop everything and help you, but I'll do my best. If that's what you need, so you can come in and get some help. But
20 minutes to work out, like
I know, but I fill up my time. But I'll do everything I can to stop and help you when you need to come in for help.
just that's what I do the homework. I don't understand 99% of it because I just look at the letters and
It's okay. I want to help you. And I do. The nighttime tutoring is sometimes fun to come to if you have the ability to use Zoom.
I just usually just don't drive, so I have to have a parent come and get me. So.
No, I mean, in the evenings, I do tutoring from my house over Zoom.
Oh.
That's what I do. On Wednesday nights, I'm usually going from 8 to 10 o'clock every Wednesday. And it's pretty relaxed. We usually laugh a lot and make fun of each other, but it's a good place to come in and get some tutoring there. Nobody ever comes Friday mornings, and usually Friday mornings I have some time, but you can come any morning and I'll try and clear my schedule, except for Wednesdays.
Okay.
Wednesdays I have a meeting and there's no way I can help anybody. Okay?
Yeah, I'll remember that. Thanks.
Today? Really? On a third? I can't see it. There's the paper. It was moved to the 15th, so that's on Wednesday. It says 15. Oh, test moved too. I didn't even know we could test today. Yeah, I was thinking about skipping for a game. I really don't want to have to go to this. Now, you can't test. What's your grade in that class? Ooh, dude, I have like a 50. I'm like a pizza. Alright, I'm not going to my notes or pay attention. It's becoming harder to pay attention. Like, the kid's getting boring. I don't have half of my notes. I look through them and I'm like, I can't comprehend. Oh, God. Oh, hey, how was the Holland Gospel? What is it called? Shit, I could only answer some. How many? Wait, yeah. Hey, Victoria. They didn't sit on the AMC he took last year. He got like 3 or 4 questions correct, and he answered like 7. Is that accurate?
I understood number 1 and number 2. Number 2, I got it right by luck.
They ask like problems you've never seen before.
Then number 3, I don't think this is right. I think something is there.
Like the area of that shape on the left.
Did you do number 3?
Like that?
Number 4, I had no idea. Yeah, I was just like,
I didn't get number 3, number 4, and number 1. Number 2 was kind of easy. I didn't understand like the number.
There's hope in there.
There's a question about like calculating the probability, like that it touched like
Wait, Yeah, you get the work afterwards, right? You get the paperback. I want to see it. I really want to see it.
Good afternoon, class.
Good afternoon, Sheldon.
So that will be the last I will hear of those things.
I know you love that.
Not my thing. Who is that person? It introduced me to stuff I've not heard before, like that. It provoked a reaction in some classes. And when it did, I made sure they understood that it was submitted months ago. So there might have been some people in the news of late who have been reflected on particularly favorably. But I did ask my sixth period, can you separate the art from the artist? You and I had that conversation last night for a bit. But, yeah. They had some interesting things to say, ultimately. I think you and I talked it out pretty good last night. The funny thing I was asking somebody though was, if you bought a Kanye album, bought the record, or the CD or something, it's sitting in your house, you decide you want to play it because you like the song. Is that different than if you are streaming its music? So that was brought up a bit, because there is or buying a concert ticket. Probably a conversation for a different group of people. So we said, we should keep talking about this because I don't want to do physics. I'd argue that physics would be a lot easier to talk about than celebrities in public. So I'll give you guys an opportunity to ask me questions on the homework. I want to point out that we discussed number one thoroughly in first period, and I did give detailed notes in the conversation. But there is some geometric parts of number one that are incredibly important. And I tried to indicate that, I think, yesterday. I want to remind you about it, that there's some geometry there that's important. We did question number two as well. There wasn't much there. That's just the one with the car going over the hill and the dip, but I think that's just a reminder that you just need to know those things. We started, and I think we finished question number three. I can't remember. No, they just asked about the projectile portion of question number three, of which I think we talked about that yesterday. We worked part of it out. So that kind of gives you an idea of the questions that were asked in sixth period. So you guys, of course, I want to have an opportunity, to talk about homework a bit in here, like I did in their class. So if you would take your homework out, and I do want to, here, I want to try and be very careful to draw this so that the lengths are the same. They look pretty much the same to me. Do they look the same to you? So this is L, this is L, and this is theta. Now, just indicating our relative point here, I'm going to draw a line that hits the perpendicular there. This represents H. You guys see why that's true? Can you follow that okay? Do you also see that this is a right triangle with a hypotenuse length L? From the standpoint of this angle, this side is A, the adjacent side. So A plus H has to equal L, because this whole thing is L2. I'm sorry, L as well. Well, A is the adjacent side in a right triangle. So A has to be L cosine theta. So L cosine theta plus H equals L, or H equals L times 1 minus cosine theta. This is worth memorizing. It shows up a lot. Object on a string, object in a circular bowl, it just shows up a lot. It's worth memorizing. Okay, back to our problem. Emphasize this geometry a bit. I don't know, do we draw this? I draw this picture in this class? If not, I'm want to clarify something that you need to be aware of. The swing problem in that question is, it's brought up a lot, and it's all over the AP exam. And I don't mean to harp on this, but you guys do not particularly adapt well for changes. So you guys would. Sorry, let me hit record. I'd say whatever this force is probably a combination of the mom and friction. Again, we don't know the mass of the child, so we're going to leave it in terms of m. This is number 4. Now, gravity is clearly doing work on the child, right? In fact, the work done by gravity, we could calculate. It's mg times 4 times whatever the cosine of the angle of this thing is. That would tell us how much work is being done by gravity. Let's put work by gravity. And there's the work by mom, which is going to be whatever that force is, times 4 times the cosine of 180. I kind of see those as the work being done in this problem. The normal force doesn't do any work. It's perpendicular to the displacement. Now, whatever happened there, the net work is going to be equal to 1/2 m2 squared. Because that's the kinetic energy of the child at the bottom of the slide. Assuming they started from rest, this would be the child's change in kinetic energy. Good so far? Now, how are we going to figure out the work done by gravity? Well, one way to do it is just to figure out what this angle is. We've got enough information to figure out the angle. We could easily do that and get our value in terms of m. You guys follow that? Is that an okay thing to do? Because I'm going to suggest an alternate method. So do you have any question about what I just suggested you do? The alternate method is to consider that whatever gravitational potential energy the child has here, that has to equal the work that will be done by gravity. Right? That's the definition. Change in potential energy equals work, well, minus work. If their potential energy decreases, then there's positive work done by gravity. So I can just find how much gravitational potential energy the child had at the top of the slide. That's got to be this. Now, if I subtract these two things, whatever's missing is the work done by mom. Does that make sense? I understand that that's sometimes a hard thing to come to. I don't in any way suggest that this is not hard. This generally is mathematically easier, but might be thematically more complicated. But I think it makes reasonable sense. There's other things you could have done. For example, you could have figured out, using conservation of energy, maybe how fast the kid's going here if there's no work done by mom. But it's still going to equal this number here, which is just what, 20m. So before Zach puts something here that's going to probably throw us off task, is there anything I could do here to elucidate this more clearly for folks who asked about this problem specifically? Yes, sir.
So when we're saying work done by
Yeah, there's no other way to, because I'm going to assume they both both bits of force are in the same direction. It would be difficult to discern one from the other. And this problem is homework, so it's ambiguous enough where we can have this conversation. On the AP exam, they would be more specific to not make you have to make that decision.
Because when I did decide those two as separate, and I just could not figure out.
Right, and there would not be a way to, unless they gave us more information about the frictional force. Now, if they told us there was a coefficient of friction of, and gave us that, well, no, then you can discern it. Then you can figure out the frictional force and work that one out, and what's left over is still the work done by mom. Does that make sense? Go ahead, Zach.
So once you do conservative energy, you get mgh equals 1/2 of mv squared.
Stop. Several of the words in that sentence don't add up.
So what I did was, I got 18, I did mgh equals 1/2 of mv squared. And then you get 20 and equals 2, and the difference was the work divided by the mom. But when I do it, I get rid of m, and then when you have it,
Can't get rid of M. The amount of energy in the system is based on the kid's inertia. Can't get rid of M. We don't know how much force was necessary to push on the kid because we don't know M. There's no way M cancels out. Not for the answer for how much work was done by mom. You might have canceled the M out by setting the wrong things equal to each other. But right now, the way this is listed, the way this is stated, you would say that the work done by gravity plus the work done by the mom has to equal 1/2 m times 2 squared. And the m done by gravity, we just said, is m times 10 times 2 plus the work done by mom equals 2m. The m does not cancel out here. Fine? Is that what you said?
yes, yeah.
Okay, fine. There's connotation with the word fine, not good ones. But I'm going to assume that that's not what you intended. But you have to have in terms of M here. All right.
The mom were not there.
The mom were not there, and we want to figure out how fast the kid would be traveling. We can do that without having M. We know a lot about this problem. If we just wanted to know the speed of the kid at the bottom, I would do this as a straight conservation of energy problem, where the kid has gravitational potential energy at the top of the slide and no kinetic energy. We're looking at top of slide. And at the bottom of the slide, if we assume that again, we'd have to assume there's no friction to do this. If there's friction, all bets are off. But I think because of the way the next question is worded, we're to assume there's no friction here. At the bottom, there'd be no gravitational potential, and we'd have all kinetic. So this would be mg times 2 equals 1/2 mv squared. In this circumstance, because we're not looking for an amount of energy, nor are we looking for an individual force, the m will cancel, allowing us to get an expression for the velocity, probably a numerical answer for the velocity, in fact. In fact, I think we do. 2 times 10 is 20, times 2 is 40, so looks like our velocity would be the square root of 40, or, I don't know, a little bit more than 6.3. But we know that at the bottom they're only actually going 5. Is that right?
Yeah.
So is the next one find the work done by friction?
Yeah. How much work is done by friction?
Okay, so that's the same problem we just did. We just, instead of we have just the mom, we do work done by friction. Does that make sense? Owen? So I'm going to do part of that because I think it's worth looking at perhaps a different way to talk about this. At the top of the slide, we had all gravitational potential energy. At the bottom of the slide, we have kinetic energy, but we're told that the slide had friction. One way that some people talk about this is to try and trace the energy. And so they want to compare the two energy states, and they would like to do so in a manner that still looks like conservation of energy. You can do it that way. Meaning I could write that on this side, the potential energy that we started with has to equal all of the forms of energy that existed at the point where the child makes it to the bottom of the slide, which includes the fact that the child has kinetic energy and the slide is now warmer because his butt slid across the top of it, and the energy that would have gone into kinetic went into warming up the slide. That has to be the work done by friction. Some books teach it this way, and there's nothing wrong with that. Some other books teach it where you say that the gravitational potential energy minus what's going to be taken away by friction will leave a certain amount of kinetic energy at the end. Remember, you have to account for all the energy. One way or the other, you're going to have to understand that the energy is conserved. It's somewhere in the problem. And that's always going to be true. So regardless of how you conceive of this, if you start with a certain amount of energy, you should be able to figure out where all of it went by the end of a problem. In the case of this problem, I'm going to use this formulation here just because it's easy. We start with mg times 2. That's how much energy the kid has. When they're at the bottom of the slide, we're told he's traveling at 5 meters per second. These things are not equal. All right, you look them up real quick. This side, 5 squared is 25, half 25 is 12 point, whoops, that looks terrible. That's 12.5 m. The left side, 2 times g is 20 m. These are clearly not equal. Well, where did the other 7.5 m go? That has to be the work done by friction. That will make them equal. That's where the other energy went. If that energy wasn't there, then it needs to stay with the kid. And that's why he'd be traveling 6.3 meters per second. But because friction took the energy out of the system, he's traveling slower. When his mom took energy out of the system, he was traveling even slower. Because there was not enough residual energy for him to be traveling the 6.3 he would be traveling if everybody would just get out of his way and let him slide with all reckless abandon. If we assume that this is the amount of work done by friction, then the work done by friction is still going to be the frictional force times the displacement along the slide times the cosine of 180 degrees. Be careful here. This, because of the way we got it, is a magnitude. We know this, the work actually done by friction was negative on the boy and took energy away from the boy. You follow what I'm saying? We have to make a conscious decision to understand that this was just how much energy was taken away by friction, but the work done by friction is negative on the boy. So this would be 7.5 m equals F times 4 times the cosine of 180 degrees. If you don't do that, you'll get a negative value for F, reminding you that the friction opposed the direction of motion. It's not a big deal. I'm just trying to make sure we're aware, we're thinking about this and being careful. We don't just throw around negative signs. Negative signs are going to have a meaning. Let's make sure we understand what that meaning is. This is how you do it then. So the average frictional force would be 7.5 m over 4. Friction is path dependent. The longer the slide is, the more distance friction has to act on the person. A shorter slide would probably mean that they're going to travel faster. Remember, the steepness of the slide doesn't matter. I can make the slide very steep and there'd be a lot less friction. It'd still hit the ground at the same speed if there was no friction, but friction is path dependent. The longer you push something along a surface, the more friction is going to take or change your system. It's path dependent. That's not true about gravity. You're not in this class. Why are you asking questions? No, go ahead.
So if you get rid of, how do you get rid of the cosine 180?
Cosine 180 is negative 1.
Okay.
So I put it here so that I would be able to cancel out the negative sign here.
Oh, okay.
But ultimately, it's a reminder. What I'm trying to do is make sure you are consciously thinking about the fact that work is a scalar value made up of vector values. And so I'm always trying to make sure I make us think of the force, the displacement, and the angle between them whenever we are thinking about calculating work. So this is the roller coaster question, which I believe is number 3, and we're talking about doing a subset of it. So here's our roller coaster picture. That's not our roller coaster picture. Let's try and draw the roller coaster picture. And I know there's some specifics. This is 30 degrees. This is half a meter off the ground. The ball here is traveling at 4 meters per second. Is that right? Okay. So, and this is the radius is 0.5. Okay. So now I need the particulars. What is their particulars about question E?
So it says instant friction is not neglected. For the car to actually reach point C, it must begin at a height of 2 meters above the ground. What is the work done by friction?
Okay. And is C here? Okay. So here's what here's the way I'd like to explain this. Right now we have an ideal amount of energy at this point, right? You've figured out how high it starts to have the amount of energy it has here. Do you understand what I'm saying? So let's figure out how much energy that is. It's 1/2 mv squared plus mg times h. And this is how much energy it has to have when it reaches that point. Now, did they give us the mass or no? Okay. Now, when you did this, you probably were able to figure out how high you were supposed to start it, and you got a numerical answer because it equaled mgh for the starting position. Now there, what was this h? I assume it's less than 2. 1.8? Excellent. Now, clearly, starting it higher means I need more energy. Right? They're saying that this is not enough. So the amount of energy I actually have when I get to the end is this amount. But to get there, I have to start at 2 meters above the horizontal, not 1.8 meters. Well, this is going to be greater than 1/2 times m4 squared plus mg times 0.5. Right, we can empirically show that right now if we really want to, but it's got to be greater. So whatever I have to add to this to make this equal has to be the work done by friction. Do everybody follow that? We're trying to trace the energy here. Now, this apparently just equals mg times 1.8. So we have some discrepancy. So should I handle the discrepancy real quick? I will be happy to handle the discrepancy real quick. I think to handle the discrepancy, we're going to look right here. And I'm going to put a big old question mark here because we're not sure. So let's handle this discrepancy. 1/2, oh no, let's not do that. 4 squared is 16 and half of 16 is 8m plus 10 times 0.5 is 5m. And that has to equal m times 10 times h. I can get rid of all the m's, I believe. And I can solve for h, and it looks like h is going to be 1.3. So I will quietly, to not draw much more attention to this, replace that with a 1.3. And now I'm thinking the work done by friction has to equal mg times 0.7. It is dependent on the mass of the roller coaster car. That shouldn't surprise you. Things that are more massive generate a larger force of friction because it increases the normal force. But you could write that as 7m if you want. I'd be okay with that. If they give you some numbers, then you can sub in for G. Now, again, why is it negative? We're talking about magnitudes here. This is the amount of work. The work done on the cars would be negative because it's taking the energy away from the roller coaster cars.